Good morning, everyone. My name is Jai Zhang. I also go by Joyce. I am a PhD student at the University of Pennsylvania. Unfortunately, because of a delay with the process of my visa application, I'm not able to attend the conference and present this work in person. However, I am extremely grateful for the conference organizer who allows me to play this recording, in which I will share with you about this exciting work that we did that involves using machine learning and NLP to analyze peer feedback. So without further ado, please allow me to present you this work titled Automated Multi-Dimension Analysis of Peer Feedback in Middle School Mathematics. This work is done in collaboration with researchers at the University of Pennsylvania, University of Denver, and QThink, the learning platform where we collected the data from. So, peer review, as many of you know, is an important pedagogy that has been increasingly adopted in classrooms to facilitate collaborative learning with the goal of improving students' communication skills, domain knowledge, and cognitive engagement. Positive learning effects have been found for both students who receive feedback and students who provide feedback. For students who receive feedback provides evaluation on students' current performance. So students who receive them are expected to learn from implementing the feedback and revising their work accordingly. And for students who provide feedback, they are expected to learn by engaging in self-reflection in which they monitor their own understanding and repair misconception as they evaluate others' work. However, without proper scaffolding, the quality of peer feedback can vary, and the effectiveness of peer review can be influenced by the quality of the feedback, impacting the learning experience and outcome for both feedback provider and receiver. As such, many studies have been conducted to understand what qualities or attributes make peer feedback more effective. So in Shu 2008, based on empirical evidence, she shows that feedback is more effective when it is specific, actionable, descriptive, and focuses on the task. And in addition to the characteristic of feedback that we just mentioned, Haiti and Timberley proposed a 4-level model outlining the 4 areas of learning a feedback can be commenting on. And they suggest that feedback should focus on more than one aspect of learning. Specifically, the feedback should evaluate on the product, process, and the progress of learning. So for example, when evaluating on a student's work, a high quality feedback would not only involve the evaluation on whether the answer is correct or not, but also on how the correct answer is derived or why the student got the question wrong, etc. And based on these understandings, evaluative criteria have been designed and are introduced in peer review activities to scaffold peer feedback. However, despite the fact that these criteria are introduced, it is oftentimes difficult to monitor if students actually follow the criteria. And therefore, in the current study, we explore the possibility of developing automated detectors that automatically detecting key attributes of peer feedback using natural language processing tools and machine learning models. With the help of these detectors, we're hoping to implement them in the platform so that they can provide adaptive intervention that scaffold peer feedback to support students in generating more high-quality reviews and comments. And here is an overview of how we develop these detectors. As shown in the graph, we first collected peer feedback from a math digital learning platform called QThink. We analyzed the feedback and identified 3 attributes that are particularly relevant and salient in the dataset, which are commenting on the process, commenting on the answer, and relating to self. We then extracted features from this feedback using 3 different NLP approaches, including bag of words, semantic and sentiment tagger, and sentence embedding. For each set of features extracted, we trained a neural network to make predictions on each of the 3 attributes. We then reported and compared the model performance across these approaches. So in this study, the digital learning platform QThink was implemented at a middle school. The platform focuses on enhancing students' math problem-solving skills by encouraging them to engage in self-regulated learning and to develop math language to communicate problem-solving process. To this end, the platform structures a math problem into a thinklet, which scaffolds the problem-solving process into 4 phases, which are understand, plan, solve, and review, as you can see in the screen shot. In each phase, students are prompted to answer various questions and to complete different tasks. For example, in the understand phase, students are prompted to answer the question of what do you notice, what do you wonder, and for these questions, students are encouraged to provide text-based responses. For another example, in the solve phase, students are provided with a whiteboard and tools such as number line and tables to demonstrate their solution. After solving the problem using the whiteboard, students are asked to record a screencast, narrating their problem-solving process and explaining the solution. In the review phase, students are asked to enter the final answer and to check their work. Once a student has completed a math problem, the thinklet that consists of the student's final answer, textual responses, and the screencast is shared with peers to review. While reviewing the responses and the screencast, reviewers are encouraged to annotate the work by providing a text-based comments describing if they agree or disagree with the work and explain what they like. These comments are then sent back to the thinklet author for possible revision. In the current study, we collected all the comments students provided to each other during the spring semester of 2021. In total, 229 comments were collected from 63 students commenting on 170 thinklets created by 117 authors. On average, each reviewer provided 3.6 comments and each thinklet received a 1.3 comments. With this data, comments collected, we're proceeded to building the detectors, which includes the following 4 steps. And these are construct operationalization, labeling the data, feature distillation, and training and evaluating the models. For construct operationalization, we first reviewed all the comments collected, understanding what information is included in this feedback. After reviewing the comments, we identified 3 attributes or constructs that are salient in the data and pedagogically relevant to detect, which are commenting on the process, commenting on the answer, and relating to self. So commenting on the process as a construct intends to reflect feedback that focuses on evaluating how a math problem is solved, specifically how mathematical operations are used to derive an answer. So for example, in this feedback, we see this student says that I like how you had 20, then subtracted 12 and got 8. And this would be an example of commenting on the process. And on the other hand, commenting on the answer is where the reviewer focuses on the outcome of the problem, assessing what the answer is and whether it is correct. So an example would be, I like how you organized it, but I respectfully disagree with your answer. So the reason that we choose these 2 constructs is because these 2 constructs identify a difference in the focus of a comment described as the first 2 levels in the Haiti and Timberley's 4-level model, which is product versus process. And it is also worth noting that these 2 constructs can both occur in the same comment. We then identified and operationalized relating to self, which is the 3rd construct. This construct intends to capture the self-reflection behavior when students provide feedback. So as a construct, it identifies behaviors when learners judge another student's work by relating it to his or her own work, reflecting on how the peer's work is similar or different from themselves, either on the problem-solving process or on the results. So for example, the student writes, "Oh, you're right, because I got the same answer." Or another student could say, "My strategy is like yours because I also did 3 times 2. And these 2 would be a perfect example to show how relating to self looks like in these comments. After the operationalization of this construct, we proceeded to coding the data. To ensure reliability, two coders coded the same set of clips separately and compare their coding, and acceptable kappa has been reached for all three constructs. And once we have the reliability established, we labeled all 229 comments collected, and these labels were then used as the ground truth to train the machine learning models. Now that we have the ground truth, we proceeded to extract features. So we started with bag of words as the simplest NLP approach. Bag of words examines the frequency of words included in an utterance and uses the frequency to understand the sentiment or semantic meaning of a sentence. So in our study, we first stamped and removed common English stop words from each comment. We create a set of features using the unigram and bigram methods. As the name suggests, the unigram method essentially treats each unique word as a vector and uses these vectors to create a frequency table. And the bigram model treats any two adjacent words as a word pair, which constitutes a vector in this case. So the frequency table denoting the number of times a word or a word pair is used in the comment is then used to train the model and make predictions. The second approach we used was part of speech, semantic, and sentiment tagging. This is another commonly used NLP technique that categorizes and counts words in a corpus based on the part of speech, semantic, and sentiment groupings. In the current study, using these taggers, we extracted a set of features that are designed to reflect the content, linguistic characteristics, and the sentiment in students' comments. In total, 22 features were extracted, including features that reflect the number of words, number of times the first person pronouns are used in a comment, and if the comment contains a question, etc. Lastly, we use sentence embedding to distill features. So sentence embedding as a more advanced technique encodes sentences into a high-dimensional vector space using the relationships of words learned from previously encountered sentences. So in that way, it is better at representing the semantic meaning in text. So we encode each feedback using TensorFlow Universal Sentence Encoder Large V5, which generates a 512 dimension embedding based on each word in a sentence as well as the words surrounding it. And these embeddings, as we can see in the slide, are then used as features to train the model and also make predictions. Using the labels that we hand-coded and feature distilled from each method, we trained a neural network model with one hidden layer to predict the probability of each attribute in the feedback. To ensure our model is generalizable, we evaluated the model with 5-fold student-level cross-validation. We computed the AUC-ROC for each testing fold and calculated the average AUC across the 5 testing folds. And here is the result of the model. Overall, as we can see from the figure, models that use sentence embedding substantially outperform the other approaches on all 3 attributes. So in particular, with this approach, the average AUC-ROC is 0.9 for commenting on the process, 0.96 for commenting on the answer, and 0.96 for relating to self. For future work, as I mentioned in the beginning, that we're really hoping to implement these detectors in the platform to allow real-time detection. And with this detection, we're hoping to provide automated suggestions, reminding students to include certain components in their comments. We're also planning on conducting scalable analysis on peer review. So for example, by correlating these detectors, the result of these detectors to other data sources such as surveys, it will be possible for us to examine what motivates students to provide certain types of feedback. it will also be possible to study if contextual features in the learning content, for example, influence which types of feedback students provide, and those topics would not be possible with smaller scale data sets. And that is everything I have. I would like to thank my collaborators for their support and ERDA for funding the project. And really grateful for conference organizer who allows me to play this recording. And I would like to thank Dr. D'Angelo for helping me deliver this presentation. So since I won't be able to attend the conference in person, I would appreciate if you can send me an email if you have any questions, suggestions, or feedback. And at this point, I'm sure you all know how much I love feedback, so please reach out. Thanks again, everyone, for listening, and I'll be looking forward to your feedback. Thank you.